class I will explain a problem of stress-strain relationships in a three-dimensional stress system using Hooke's law. How we can find out the stresses given knowing the strains. The problem runs like this. Following strains exist at a point in a three-dimensional system. Determine the equivalent stresses at that point. He has given the values of X modulus and Poisson's ratio E and mu values. The strain values are given like this: epsilon x, epsilon y, epsilon z. They are the normal strains, and shear strains gamma x y, gamma y z, and gamma z x. So as you know, strains doesn't have any unit, so just they are numbers. So let us write down the generalized Hooke's law, the Lami's equations, to find out the stresses. So the equations are like this: sigma x is equal to 2g epsilon x plus, so 2g epsilon x plus you have lambda into e into epsilon b, lambda into e into epsilon. So this equation we have just derived in the earlier video class. You can just refer that. So the second equation is sigma y is 2g epsilon y plus lambda into e into epsilon b. The second term we make the same. Third stress term is sigma z 2g epsilon z plus lambda e into epsilon b. So these are the normal stresses or the direct stresses. You have three components of shear stresses also. They are tau xy, which is nothing but g into gamma xy, then tau yz, g into gamma yz, and tau into zx, which is g into gamma zx or xz. So these three are the shear stresses. So at a point in a three-dimensional stress system, you have six components. So these are the six components. Now let us see. So all the strain values are given. E and mu values are given. We need to compute these two constants, that is g and lambda. So g is the shear modulus, which is given by, you know the relationship between E and G. So G is given by E divided by 2 into 1 plus mu. E divided by 2 into 1 plus mu. That is E is 2G into 1 plus mu. From that we can get. So this is 200 GPa divided by 2 into 1 plus mu is 0.3. So if you simplify this, you get the value of rigidity modulus. So which is 200 divided by 2 divided by 1.3, it is 76.92 76.923 GPa gigapascals. Okay. Then Lami's constant lambda is the Lami's constant. So Lami's constant depends on the value of mu. So in the last class I have derived the expression for Lami's constant, which is mu divided by 1 plus mu into 1 minus 2 mu. So this is the Lami's constant. Mu is 0.3 divided by 1 plus 0.3 into 1 minus 2 into 0.3. So if you simplify this, so it is 0.3 divided by 1.3 into 1 minus 0.6, that is 0.4. So if you simplify this, you will get 0.3 divided by 1.3 divided by 0.4. So you are getting 0.5769. Since it is a very small number, you can just have 4 digits. So these two are the constants we need to find the stress values. Now let us see how these stress values are found out. Just substitute in these 6 equations, you will get the stress at that point, all 6 components. So one by one we will find out. Sigma x is 2g sigma epsilon x, that is 2g into 2g is 76.923 into epsilon x he has given 0.003, substitute that value, plus lambda is 0.5792 into E value is 200 GPA. Let us keep all the values in GPA only, into epsilon v. So epsilon v, of course we need to compute. Epsilon v is the volumetric strain, which is the sum of all the three linear strains. In this case, epsilon x plus epsilon y plus epsilon z is epsilon v. So epsilon x is 0.003 he has given, plus epsilon y is 0.308, plus epsilon z is 0.307. Now if you add these three, you are going to get epsilon v 0.003 plus 0.308 plus 0.307. So the value is 4.5 into 10 power minus 3, or you can write it as 0.0045. So that is the value of epsilon v. Now substitute that value of epsilon v here, 0.0045. So if you simplify this, that is the value of sigma x in GPA. So 2 into 76.923 into 0.003, so plus 0.5723 5792 into 200 into 0.0045. So the value is 0.9828 GPA. 0.9828 GPA. If you want to convert this into MPa, that is Newton per mm square or megapascal, multiply by this by 1000, 982.8 MPa. This is the answer. Okay, 982.8 MPa. Now, second value sigma y, that is the stress in the y direction, normal stress in the y direction, 2g epsilon y. 2g once again is same. So only this, instead of epsilon x, you get sigma x. Sorry, epsilon x will get epsilon y here, 0.308 plus this term remains same, 0.5792 into 200 into 0.0045. Now if you simplify this, so it is 2 into 76.923 into 0.308 plus 0.5792 into 200 into 0.0045. So the value is 0.64436 GPA, or we can call it as 644.36 MPa. This is the stress. Next, sigma z. Sigma z is 2 into g into epsilon z. So g is once again 76.923 into epsilon z is 0.307 plus this term remains same, 0.5792 into 200 into 0.0045. So if you simplify this, you will get 2 into 76.923 into 0.307 plus 0.5792 into 200 into 0.0045. The value is 0.62897. 0.62897 GPA, or into 1000, that is 628.97 MPa. So these are the normal stress values at that point. Now shear stresses, so we are going to get as tau xy, which is g into gamma xy. Just multiply rigidity modulus by gamma xy, you get tau xy. So G is 76.923 into gamma xy has given 0.0301. So it will be I think point 76.923 into 0.0001 will be 7.69 into 10 power minus 3. Okay. So GPA. So this is GPA. If you convert MPA into 1000, that means 7.69 MPA. This is the value of tau xy. Next, we need to find tau yz. So shear stresses always act tangential to the plane. This is the shear stress acting tangential and xy plane. This is yz plane. G into gamma yz. So G is 76.923 into gamma yz has given 0.305. So if you multiply that, so 76.923 into 0.305 will be equal to 0.03846 GPA, or into 1000 means 38.46 MPa. So this is the value of that is tau yz. Then tau zx, we give the tangential shear stress in zx plane. G into gamma zx 76.923 into gamma zx is 0.302. So if you multiply this and this, 76.923 into 0.302, it is 0.01538. 0.01538 GPA, or it is 15.38 MPa. So these are the shear stress values. These are the normal stress values. Of course, we can always write this in the form of stress tensor at that particular point. Sometimes I may ask you to write in the stress tensor form. You know that the stress tensor at a point, stress tensor at that point, it is written like this. It is written like this: sigma x, sigma y, sigma z as the principal diagonal elements, and here you will be having tau xy, tau xz, and it is symmetric, therefore it is tau xy, tau xz, and here you will be having tau yz, and here tau yz. So please note that tau xz is the same as tau zx, tau xy is the same as tau yx, and tau yz is the same as tau zz. So this you should be knowing. Now once you substitute these values, whatever we have got in this stress matrix, stress tensor, then that completes the problem. So sigma x I have written first 982.8. First element is 982.8. Then sigma y is 644.36. 644.36. Then sigma z is 628.97. 628.97. Then coming to the shear stress values, tau xy is 7.69. So I will write here 7.69. This is symmetric, therefore this also 7.69. Tau xz is 15.38. This value is 15.38. This value is also 15.38 because it is symmetric. Please note that both the stress and strain matrix tensors are symmetric. Then here I have written tau yz. Tau yz is 38.46. 38.46. This is 38.46. All the values are in megapascals or Newton per mm square. So this is the stress tensor at that point where the strains are given. So by using stress strain relations or Lamy's equations, generalized Hooke's law, you can always find out the stresses by knowing the strains in a triaxial stress system. This is an example.